Okay, so now we'll talk about consumable power storage. Ayo, okay, so this is a Ragone plot of electrochemical devices. Consumable power sources. This is taking the power source with you into space. This spread of consumable power sources range from fuel cells to capacitors, where we're looking at the change in energy density with power density. So energy is the total duration, whereas power density is the amount of charge you can dissipate at once. So you'll see here that fuel cells are really energy dense. So this will be for longer lasting missions, but they're not as power dense, so they can't discharge as quickly. Whereas we have something more moderate with lead acid, nickel cadmium, and lithium batteries. On the other side of the spectrum, we have capacitors, which are not energy dense, so it doesn't pack as much energy for an overall mission, but it can discharge quite quickly. So a question, is fully charging and fully discharging, do those processes take the same amount of time? So yeah, charging and discharging take the same amount of time. Short answer. Let's start off with fuel cells, which was the most energy dense form. Fuel cells are based upon chemical energy. One of the most common fuel cell chemical compounds is a hydrogen fuel cell, where you have H2 and O2. You have a bank of H2, you have a bank of O2, and when they come together and join at electrolyte, they have an electric potential difference that generates electricity. The production of electricity is solely dependent on the availability of hydrogen and oxygen. So when the fuel is gone, the ability to produce electricity disappears as well. Here you'll see the Apollo fuel cell. The Apollo command module's primary source of electric power was from a set of 3 fuel cells housed in the service module. Each fuel cell combines hydrogen and oxygen to produce electricity and water. The water was used for drinking by the astronaut crew. Each of the fuel cell power plants contained 31 separate cells connected in series. Each cell has hydrogen and an oxygen compartment, and electrodes and in combination produce 27 to 31 volts. Normal power output for each power plant is 563 to 1420 watts. We also see here the space shuttle fuel cell. And then here's a question. Water can be electrolyzed into molecules with excess power as a form of regenerated fuel. This seems inefficient. Why wouldn't the extra water simply be kept for astronaut use, or if the mission is uncrewed, the fuel cell redesigned so that no excess power is produced? So yeah, it can be certainly used for astronaut crewed consumption, like it was for Apollo. You can also take the water that is a byproduct of this fuel cell process, and if you have excess electricity, you can re-separate the H2O2 into H2 and O2 and put them back in the fuel tank to reuse again. But there is some power loss associated with that because things are not totally efficient. But yeah, there are ways that fuel cells can be more efficient. Okay, on the other side of the spectrum, we've got capacitors, which are very power dense, but not very energy dense. Let's see. Here is how a capacitor generally works, so it's based on electrical energy. There's an electrical field. A capacitor is made out of two conductive plates, and when there is some voltage, a capacitor can charge and build up charge on one conductive plate so that it's accumulating a higher potential, and then when it's time to discharge, that higher potential can just cross this dielectric and dissipate charge, which can, produce current. So capacitors can go both ways of charging, discharging. They are used typically for smoothing over any kind of like surprising power outages. For example, in cube satellites or just satellites in general, if you need your computer to stay on and you enter an eclipse, you can use a capacitor to smooth over that time when the computer doesn't have power generation. This is just a way to wean you over until you can have power generation again. There are these innovative little Sprite spacecraft that are about this big, and they use capacitors as an energy storage device. Given that the spacecraft is so small and a capacitor is not very energy dense, the amount of energy that a little capacitor can keep can act as a battery. If you have just a very slow discharge, you can maybe make it through with just that little amount of energy. All right, a little bit about capacitors. In comparison, we're going to talk about lithium-ion batteries in a little bit, but lithium-ion cells typically have an energy density of about 150 watt-hours per kilogram. Supercapacitors have between 5 to 30 watt-hours per kilogram. So that's about 5 to 30 times less energy density than a lithium-ion battery. Capacitors can act as a consumable power source when charged and connected to a load, also act as an energy storage option. We'll talk about power conditioning later, and that's where capacitors really shine, where they're doing that power smoothing action. Okay. So another type of consumable energy, the last one we'll talk about in this little section, is the primary battery. We know batteries just like as this general spectrum, but there are two classifications that are important to talk about. Primary batteries are consumable. They are one-time use. So like once you start using it, you kind of just drain it. There are some that you can intermittently like pause, but for the most part, once you start using a primary battery, you just go. Whereas a secondary battery is rechargeable. Talk about that in a little bit. Okay. Primary batteries store a finite amount of energy and discharge until energy cannot be withdrawn. Although consumable, primary batteries are typically higher in energy density, which may be preferred for short space mission lifetimes for their reliability and simplicity. Primary batteries are evaluated by the energy density, discharge rate, and temperature limits. And these things are dictated by battery chemical compositions. Primary batteries are typically used only on spacecraft that are planned to operate for only a short amount of time, even if they must travel for a long time before being activated. Generally, primary batteries also, while they're sitting and not being used, discharge less than secondary batteries. And I wanted to show you all the different spacecraft that primary batteries have been used in. It goes all the way back to Sputnik, but you can see more recently, let's just look at the type of satellite that the primary batteries are used in. So Sputnik We all know Sputnik, we love Sputnik. Then we look at like impactor, probe, orbiter, rover, lander, aerobot, rover, lander. So you can see that the type of spacecraft primary batteries are used in are these like finite mission, they're like higher risk, shorter lifetime sorts of missions. Yeah, because they're higher risk, because power is so important, you just want to make sure like you definitely have some time to do your science, even if it's a finite short amount of time. Okay, I thought it'd be nice to go over battery terminology because if you're going to use batteries, you should probably know how to evaluate them. So amp hours, that's the total capacity of a battery. You can think of it as the amount of current per time duration, where amps are your unit of charge, hours your unit of time. Your depth of discharge is some percentage value associated with battery capacity. So 75% depth of discharge means 25% capacity remaining. Let's see. The percent depth of discharge can be calculated with 3 different variables. Your watt-hour load, which is the amount of watt-hours delivered to the load, your capacity of battery in amp hours, and the average battery discharge voltage. We're going to talk about battery cycling in a bit, but to prolong battery lifetime, you want to limit your depth of discharge. Watt hours is the stored energy of battery. So that relates to amp hour in the way that you multiply amp hour by the average discharge voltage. Charge rate, or C rate, is the rate at which a battery can accept charge. Typically, you want to charge and discharge at this rate. So the total capacity of your battery divided by 15 hours.